We'll start in about 3 minutes. All right, today we'll start reviewing for test 2. We'll go over the review for test 2 sheet today. So I don't know when we're going to finish it, but if we do finish it and there are still days left, then we'll start the test review sheet after that. This first problem is from section 7.7. That's the section where you learned about the Simpson's rule and trapezoidal rule to estimate definite integrals. So we'll create a table of input and output values for f of x, defined to be 420 over x. For x values from 1 to 7, and so we'll just find the f of x values for the integers from 1 to 7. Okay, so when x is 1, f of 1 is 420 divided by 1, or 420. F of 2 is 210. F of 3, 420 divided by 3 is 140. F of 4, 420 divided by 4 is 105. F of 5, 420 divided by 5 is 84. And then f of 6, 420 divided by 6 is 70. And f of 7, 420 divided by 7 is 60. So for n equals 6, we have 6 subintervals. And note that delta x is equal to 1. So the Simpson's approximation for n equals 6, we have delta x over 3, so 1/3, and then times f of 1, which is 420, and then plus 4 times f of 2, 4 times 210, then plus 2 times f of 3, or 2 times 140, then plus 4 times f of 4, or 4 times 105, plus 2 times f of 5, or 2 times 84, and then plus 4 times f of 6, or 4 times 70, and then plus f of 7, which is 60. So whatever that number is, I'll let you do that. That's pretty simple to add up those. Just remember the Simpson's rule formula for estimating a definite integral. You can review that in the textbook if you don't already have it memorized. Then the trapezoidal rule. So t sub 6, out front for the trapezoidal rule, we have delta x divided by 2. And since delta x is 1, we have 1 divided by 2. And then f of 1 is 420. And then plus 2 times f of 2, 2 times 210, plus 2 times f of 3, 2 times 140, plus 2 times f of 4, or 2 times 105, plus 2 times f of 5, or 2 times 84, plus 2 times f of 6, or 2 times 70, and then plus f of 7, or 60. Okay, so add those numbers up for the trapezoidal approximation. Then in this part, this integral, you can evaluate it and then use a calculator. So I'll do that up here. What's that?
You can use a calculator on this test?
No, this is just, we're just going to demonstrate how close the Simpson's rule approximation and the trapezoidal approximation is to the actual integral itself. Okay, but by hand we can evaluate the integral of 420 over x dx from 1 to 7. So the antiderivative is 420 times the natural log of x, and we evaluate that from 1 to 7. So we get 420 times the quantity, the natural log of 7, minus the natural log of 1. The natural log of 1 is 0. So 420 times the natural log of 7. So just for your own curiosity, you probably should do it just for the sake of the problem. Use a calculator, find a decimal number for the natural log of 7, multiply it by 420, and compare that to the approximations using Simpson's rule and the trapezoidal rule, and note which one gives the better approximation. Okay, moving on. The next problem. For what values of p does this improper integral of 1 over x to the p dx from 1 to infinity, for what values of p does that converge, and for what values of p does it diverge? So one day, a few weeks ago, we proved that this converges when p is So for Friday's test, you don't have to prove it, but you do need to know it. For what values of p will this improper integral converge when it goes from 1 to infinity? Well, when p is greater than 1, it converges. And it diverges when p is less than or equal to 1. So make sure you remember that. And then on this one, evaluate the improper integral of 1 over x to the 5th dx from 1 to infinity. So we know even before evaluating it that it's going to converge because the exponent 5 on x in the denominator is greater than 1. So we know that it converges. Remember what to do for this type of improper integral. We write it as a limit as b approaches infinity, and then we'll write a definite integral from 1 to b. So b represents a real number, not infinity, but b is going to go to infinity. Let's rewrite 1 over x to the 5th as x to the negative 5 dx. Then the limit as b approaches infinity, an antiderivative of x to the negative 5. Well, if it helps, you can just write it in using the formula x to the negative 5 plus 1 divided by negative 5 plus 1, which we will evaluate from 1 to b. 1 to b, the limit as b approaches infinity. Okay, so negative 5 plus 1 is negative 4, x to the negative 4. And in the denominator, negative 5 plus 1 is negative 4. So let's think of this as negative 1 over 4x to the 4th in the denominator, evaluated from 1 to b. So the limit as b approaches infinity. So we get negative 1 over 4b to the 4th. So negative 1 over 4b to the 4th. And then we're subtracting the negative of 1 over 4 times 1. So just a couple of more steps. So we get negative 1 over 4b to the 4th plus 1/4. And now we can take the limit. So this term, negative 1 over 4b to the 4th, as b approaches infinity, this approaches 0. So the limit is 0 plus 1/4, or 1/4. Okay, be able to do that for the test. Okay, on the next page, more about improper integrals. So for these first two, use the comparison test to determine if the improper integrals converge or diverge for the first two. Okay, so the improper integral of dx over the square root of x to the 4th plus 2x plus 3 from 1 to infinity. So how about this? For values of x greater than or equal to 1, the square root of x to the 4th equals x to the 2nd. You'll agree? Okay, well, if inside the square root I add 2x plus 3, square root of, this is a square root of a larger number, that should be greater than x to the 2nd. Are we in agreement? Okay, then remember, if a positive number is greater than another positive number, when you write the reciprocal of the greater number is going to be less than the reciprocal of the other number. Okay, so now we can apply the comparison test. So this improper integral, since this is the integrand of this improper integral, since this expression is less than 1 over x squared, then this improper integral will be less than the improper integral of 1 over x squared dx from 1 to infinity. And what do we know about this improper integral? 1 over x squared from 1 to infinity? Yeah, it converges. And since this improper integral is less than that one, it also converges. If this is equal to a finite number, then this one has to be equal to a finite number also. Even if we don't know what that finite number is, we do know that it converges to a finite number by the comparison test. Okay, so the improper integral of dx over the square root of x to the 4th plus 2x plus 3 converges. And that's all we're supposed to find. It doesn't say to find what it converges to, just determine if it converges or diverges. Okay, with a little practice, you'll know ahead of time what to expect. You know, in this denominator, the term with the largest exponent is x to the 4th. So x to the 4th is a dominant term for values of x when they approach infinity. So it's pretty close to looking like 1 over the square root of x to the 4th or 1 over x to the 2nd. And we know that for 1 over x to the 2nd, that improper integral converges. So that's how you can gain inside information on how to verify for certain whether it converges or not. Okay, the next one, the improper integral of x plus 1 over the cubed root of x to the 5th minus 1/2 from 1 to infinity. So what might you suspect ahead of time on this one? There's a question I just noticed on YouTube. from the previous problem, how do I know that negative 1 over 4b to the fourth goes to 0? B goes to infinity, so this denominator gets larger and larger. So negative 1 divided by a larger and larger and larger number gets closer and closer to 0. So the limit of that term is 0. So the overall limit, 0 plus 1/4 is 1/4. Okay, on this improper integral, do you have a suspicion one way or another whether that improper integral converges or diverges?
Converges?
That wouldn't be my guess. Okay.
Diverges?
Oh, yeah, diverges. Okay, why would I suspect that?
If you divide x by x to the 5/3, then you get x to the 2/3.
Yeah, if you look at the numerator, we have x to the first plus 1, but I'm just ignoring the plus 1 because it's, for large values of x, the plus 1 is insignificant. And in the denominator, the dominant term is the cubed root of x to the fifth. So x to the first divided by x to the 5/3 would simplify to 1 over x to the 2/3, right? 1 over x to the 2/3. And so if I have an improper integral from 1 to infinity of 1 over x to the 2/3, I know it's going to diverge because the exponent is 2/3, which is less than 1. So that's what I suspect. I suspect that it diverges, but how do we go about showing it? Well, similar to what we were doing. So if I compare the cubed root of x to the fifth with the cubed root of x to the fifth minus 1/2. So these are for values of x greater than or equal to 1. So which one of those numbers is larger for x greater than or equal to 1? So the one on the left should be larger, shouldn't it? And if I reciprocate, then 1 over the cubed root of x to the fifth should be less than 1 over the cubed root of x to the fifth minus 1/2. And then if I multiply both sides by x, and x is a positive number, then the inequality is preserved, right? So if I multiply both sides by x, I'm running out of space, but I get x over the cubed root of x to the fifth. That should still be less than x over the cubed root of x to the fifth minus 1/2. So I'm going to leave this one on the left the way it is, and then on this one, I'm going to add 1 to the numerator, so this one should be less than x plus 1 over the cubed root of x to the fifth minus 1/2. But as we were discussing earlier, how do we simplify x divided by the cubed root of x to the fifth? So it's x, or it's 1 over x to the 2/3, right? When we simplify this using properties of exponents. So this is 1 over x to the 2/3. So in terms of improper integrals, the improper integral from 1 to infinity of 1 over x to the 2/3 dx should be less than this improper integral. But the improper integral on the left, since the exponent on x in the denominator is less than 1, it diverges. So this one diverges by the comparison rule, means this one also diverges. So when infinity is involved, it's sort of not proper to write that this infinity is less than that infinity, but by the comparison test, since this one does not converge to a finite number, and for every finite value x, 1 over x to the 2/3 is less than this finite number, this improper integral must also diverge by the comparison test. Okay, the next one, evaluate the integral. What kind of integral is this?
Definite integral?
It's also an improper integral. Why is it improper? At first glance, you might think, oh, this is just a definite integral. But notice the denominator has x minus 3 to the 2/3. And since division by 0 is undefined, and the interval for the integral is from 1 to 5, we have an undefined term when x is 3. So this is an improper integral. Because the function that we're computing the integral of is undefined at x equals 3, which is in that interval from 1 to 5. So for this one, we write it as a sum of two improper integrals. One of them is from 1 to 3. And the other one is from 3 to 5. So each of those is also improper because the one on the left, the integrand is undefined at x equals 3. And same with the one on the right. Okay, so we use limits again. Let's just do it one at a time. This improper integral on the left from 1 to 3. I'm going to just start writing it as x minus 3 to the negative 2/3, since we're going to do that anyway. So we're going to write this as the limit as b approaches 3 from below of the definite integral from 1 to b of x minus 3 to the negative 2/3 dx. So since b is approaching 3 from below without actually equaling 3, this is a valid improper integral. Okay, so an antiderivative of x minus 3 to the negative 2/3 is x minus 3 to the 1/3 divided by 1/3. So that's going to be, when you divide by 1/3, you multiply by 3. So it's 3 times x minus 3 to the 1/3. And this will be evaluated from 1 to b. So I'll take it to the next line. Okay, so we'll evaluate this when x is b. So we get 3 times b minus 3 to the 1/3, and then minus 3 times 1 minus 3, which is negative 2 to the 1/3. And then as b gets closer and closer to 3, b minus 3 gets closer and closer to 0. So the limit of this as b approaches 3 is 0. And we're subtracting a negative because the cubed root of a negative is a positive. So this is plus 3 times the cubed root of 2. Okay, so this limit on the left, or this, I should say, this improper integral from 1 to 3 converges to this finite number. So now we have to essentially do the same sort of thing for the other improper integral from 3 to 5. So this one, the improper integral from 3 to 5 of x minus 3 to the negative 2/3 dx. This is also the limit. I'll use a different letter. C approaches 3 from above of this integral. So the lower limit is c, the upper limit is 5. Okay, so we get the same antiderivative, which is 3 times x minus 3 to the 1/3, evaluated from c to 5. Okay, so when x is 5, we get 5 minus 3 is 2, or 3 times 2 to the 1/3. I'll just go ahead and write it as 3 times the cubed root of 2. And then minus 3 times c minus 3 to the 1/3. And now we take the limit. As c approaches 3, this term approaches 0. So this limit is just 3 times the cubed root of 2. This one has the same value as the other limit. Okay, so in conclusion, we say that the improper integral from 1 to 5 dx over x minus 3 to the 2/3 is equal to the sum of those other two improper integrals, which we have a total of 6 times the cubed root of 2. Okay, on the next page, so this one says if f prime is continuous on the closed interval from a to b, the length of the curve y equals f of x for values of x between a and b is the definite integral from a to b of the square root of 1 plus f prime of x squared dx. Okay, that's one formula to make sure you've memorized. And let's find the length of the curve of this function, y equals 5 plus 2 times x to the 3 halves, all divided by 3, on the interval from 1 to 8. But we can make it a little easier to look at if we rewrite it as y equals 5/3 plus 2/3 times x to the 3 halves. We have to find the derivative with respect to x. The derivative of the constant is 0, and so we get 2/3 times 3 halves times x to the 3 halves minus 1, or x to the 1 half. And this just becomes x to the 1 half, or the square root of x. And let's go ahead and write what 1 plus the square of the derivative is. So it's 1 plus, and then when we square the square root of x, we just get x. So the length of the curve is the definite integral from 1 to 8 of the square root of 1 plus x dx. So that's the same as the definite integral of the quantity 1 plus x to the 1 half from 1 to 8. So an antiderivative is 2/3 times 1 plus x to the 3 halves from 1 to 8. So this one's pretty easy. First replace x with 8. 1 plus 8 is 9, so we get 9 to the 3 halves. And then minus 2 to the 3 halves. So this is an okay answer, but you can take it a little further. 9 to the 3 halves is just 27. And 2 to the 3 halves is 2 times the square root of 2. So that's as far as we'll take that one. And the next problem, the arc length function for a curve y equals f of x, where f is an increasing function, is s of x equals the definite integral from 0 to x of the square root of 3t plus 5 dt. Okay, so if f of 0 equals 2, then find an equation for f of x. So recall in general, if you have a function f of x, then the arc length function for that is the definite integral from some real number a to x. And then for the integrand, you switch variables and write it as the square root of 1 plus f prime of t squared dt. Okay, so for this particular arc length function, we want to determine what f of x is. So what can we do? This is the formula for the arc length function. And this is the arc length function for a particular f of x. So we can say that the integrands are equal. We can say the square root of 3t plus 5 is equal to the square root of 1 plus the f prime of t squared. Then we can square both sides, get rid of the square root. So now we're down to 3t plus 5 equals 1 plus f prime of t squared. Then subtract 1 from both sides. So we get 3t plus 4 equals f prime of t squared. Okay, now what? Yeah, apply the square root method. So let's write it as f prime of t equals positive or negative square root of 3t plus 4. And then using the initial conditions, f of 0 equals 2, that will help us determine if this should be positive or negative. Okay, but since we have a formula for f prime, then we can find f of t by finding an antiderivative of either positive or negative square root of 3t plus 4. Okay, so if we look at that in isolation, just think about what we would do to find an antiderivative of the square root of 3t plus 4. So I'll write it as 3t plus 4 to the 1/2 dt, but I want 3 dt. So I put a 3 dt and compensate for the factor 3 by multiplying by 1/3, right? And then an antiderivative is going to be 3t plus 4 to the 3/2 divided by 3/2, or multiplied by 2/3. And then plus a constant. So we should include a plus or minus for now. Plus or minus 2/9 times 3t plus 4 to the 3/2 plus a constant. Okay, then the initial condition, we can now replace t with x. But for this part, we can go ahead and use this fact that f of 0 equals 2. So when t is 0, f of 0 is 2. So we get 2 equals plus or minus 2/9. And when t is 0, we get 4 to the 3/2 plus c. So it looks like there are two possible functions. So 4 to the 3/2 is 8. So 2 equals positive or negative 2/9 times 8 plus c. So let's just pick the positive one. That will be easier. If I ignore the negative solution, then 2 equals 16/9 implies that C equals 2/9. Okay, so let's just pick f of x to be positive 2/9 times 3t plus 4 to the 3/2 plus 2/9. Whoops, I should have made that an x. F of x is equal to 2/9 times the quantity 3x plus 4 to the 3/2 plus 2/9. Okay, let's move on to the next page. Okay, let y equals f of x be a function that is positive, such that f prime is continuous. Rotating y equals f of x for values of x between a and b about the x-axis generates the surface area. So it's the definite integral from a to b of 2 times pi times f of x times the square root of 1 plus f prime of x squared dx. Hey, but if we rotate the same function f of x from a to b about the y-axis, what's the surface area?
Well, we need to memorize these functions as well, or these equations.
Yeah, this, if we rotate it about the y-axis, instead of using f of x, it's going to be x. Because we're measuring the radius of the cross-section of a rotation. So if it goes to the y-axis, then that radius is an x value. And then times the square root of 1 plus f prime of x squared dx. Okay, let's find the surface area by rotating y equals 2 times the square root of x for values of x between 0 and 4 about the x-axis. Okay, this is our f of x. We need to know what dy dx is. So this is like 2 times x to the 1/2. And so we're just going to get 1 over the square root of x when we take the derivative of 2 times the square root of x. Okay, so the surface area, since we're rotating about the x-axis, is going to be the integral from 0 to 4 of 2 pi times our function f of x, which is 2 times the square root of x, times the square root of 1 plus the derivative with respect to x squared. So when we square the derivative, we're just going to get 1 over x. I'll go ahead and write it though. Dy dx squared is 1 over x. So this is the square root of 1 plus 1 over x dx. Hey, let's simplify a little bit. 2 pi times 2, we can write that as 4 pi, and then times the square root of x. And inside this other square root, I'm going to write 1 plus 1 over x as a single rational expression, so it will be the square root of x plus 1 over x. Hey, do you see what's going to happen next? So I'll just tell you what I'm not going to write it all down, but if we were to rewrite the square root of x plus 1 over x as the square root of x plus 1 over the square root of x, then the square root of x divided by the square root of x cancels. So let's write down the result we get from doing that. So the square root of x cancels, so we just get the definite integral from 0 to 4 of 4 pi times the square root of x plus 1 dx. And this is a fairly simple integral to evaluate. An antiderivative of the square root of x plus 1 is x to the 3 halves divided by 3 halves. So if you divide by 3 halves, that's equivalent to multiplying by 2/3. Okay, so 4 pi times 2/3 is 8 pi over 3. And then evaluate the integral when x is 4. 4 plus 1 is 5. So we get 5 to the 3 halves, and then minus, when x is 0, 1 to the 3 halves, or minus 1. Okay, so this is an okay answer if you want to leave it just like that. Okay, we have less than a minute. So let's see. Yeah, I suppose tomorrow we'll be able to finish this, the rest of this test 2 review, and then get started on the test 2 review sheet that I emailed last week. But for now, that's all for today.